Hello and welcome to Malware Analysis Part 2. We're going to be discussing buffer overflows as well as the disabling of ASLR, canary values, and NX bit. Now before we get started, some disclaimers. Obviously everything presented is my opinion. We will focus on x86, that's Intel architecture 32-bit. I am a cybersecurity enthusiast, and so this is stuff that I do in addition to my job that I just have a passion for and have a lot of interest in. Obviously, all the tools and demos that I show are for learning purposes only. Now, the source code for everything that you're going to see is going to be available on the website, as well as the links to all the videos. The session outline is we are first going to talk about buffer overflows on the pre-Nihilum architecture, and we'll look at smashing the stack with an actual exploitation there. Then we're going to talk about the countermeasures that have been put into place that are then implemented in the Nihilum architecture. That's Intel Core i7 and higher. So then I'm going to show you how you can actually disable those countermeasures, continue to do the classic smash the stack buffer overflow exploitation. So first, pre-Nihilum architecture. Basically, in the processors that are named there was no kind of randomization for memory addresses. So they didn't have any kind of protection built into the kernel against stack smashing, and that's why the classic buffer overflow was so prevalent for so long. Now in the demo, you're actually going to see some stack smashing done. The vulnerable function is going to be process data. Inside of there's a mem copy where we're basically going to overstuff it and then do our classic smash the stack, and then insert shellcode to then do a TCP bind. So without further ado, we will go right into our demo. So for this demo, we're going to look at a socket server program that allows for client connections. So the first thing we want to do is actually run the executable and just see if it is susceptible to a buffer overflow attack. Now, as you can see, the program is running here, and I've got this running on my Windows XP machine. The bind port is 9000, so that's what we're going to write in our client code from our Kali Linux attacker machine. But right now this program is just waiting for connections. Now in order to actually determine if a program is susceptible to any type of buffer overflow attack, it's best to kind of start with a large buffer, and you can actually create pattern that better identifies when the crash happens, and Metasploit can help you with this. So on your Kali Linux machine, you're going to go to the following folder, and here we're going to create a pattern that is going to be 2000 bytes long. So this Ruby script will run and basically generate for us a sensible pattern that basically gives us some kind of clue as to where we are inside of this giant buffer, right? So you can see it starts off with capital A, lowercase a, the number 0, and then capital A, lowercase a, the number 1, and so on. So we could actually take this and create a Python script, and the first Python script we're going to look at is called smashmeet find EIP at crash. If we take a look at the source code, we can see it's pretty simple. Basically, we import the socket and system libraries. We create our own socket, and of course this socket is going to connect to that Windows program over the port 9000. Now for the next part, we're going to have that shellcode that we generated be sent over to port 9000 to the program, and it actually does the sending here. It sends that buffer over, and then we'll close the socket. So once again, we just want to see if the program is susceptible to a buffer overflow attack. Now the Windows machine, its IP is 103, so I'm going to go ahead and send that over. Aha, and so what you see is that it definitely crashed. So we get this nice Microsoft message saying, hey, you know, something went wrong. And in here, you can actually see that we did indeed send over that huge 2000 byte buffer that we constructed using the Metasploit tool. So that means, this is good news, that means that this program is susceptible to some kind of buffer overflow. And so let's go ahead now to the next step to determine actually where EIP might be in the stack, so that we can get the appropriate return address to know where to place our shellcode. Now the executable for this program we can basically dump into Immunity. So it's the same program is running. Now Immunity gives us an entry point, so it stops the program for us, which is very nice. We're actually going to set a breakpoint at this location because this particular location is the beginning of a function that has vulnerable code in it. Now, how do I know it has vulnerable code? Well, it has this mem copy right here. Unfortunately, we're not blessed with seeing the source code, but if we were, we would determine that basically this mem copy inside of this process data method is going to give us the ability to overflow our stack, basically. So we're going to do a stack buffer overflow. And so so what we can do is, if we want to kind of see how this looks on the stack, we can actually step into this function. So here you can see that when we dropped in our executable into Immunity, there's going to be this program entry point where it kind of pauses. So we set our breakpoint at the position just before the stack frame, which is the beginning, of course, of our function. So we always have a stack frame set up where we push EBP, we do a move of ESP into EBP, and so on. Now we're going to go ahead and play the program, and then we're going to go to the Kali machine, and we're going to go ahead and send in our script for the smash me find EIP at crash, and we're sending that to the Windows machine. Now back in Immunity, we can see that we are now at the stack frame pointer. So we're at the beginning of our function here. You can tell that it's all in one function because you can kind of watch this little bar here. What we want to do is we want to actually step down into the function and look at some of the details here. So I'm going to step into keeping an eye on this stack over here. Let's go down to mem copy. So the mem copy, we can see it's going to do a jump, and we have passing in, we've got a source and a destination, right? So that would be the contents of the buffer, right? And then we need to kind of complete the function almost to the end. We have the leave, and then before we hit this return, we basically want to pay attention to two pieces of information. So before we leave this function, we want to keep our eyes on the value of EIP and on the value of the top of the stack. So let's go ahead and leave the function, and it's probably going to crash. Boom. Okay, so the program just crashed. So we can see that EIP is now pointing to this 69, 42, 35, 69. And the top of our stack is pointing to 37, 69, 42, 36. Now let's go ahead and copy these values out because we will need them inside of our Kali Linux machine. Okay, so what I did is I copied out those two values and placed them just in a note. So my EIP at the time of the crash is 69, 40, 42, 35, 69. And the ESP at the time of the crash is 37, 69, 42, 36. Now, why these areas are important is because we need to find out where inside of this humongous 2000 byte buffer that we created, where in here our EIP got overwritten, right? And so how we can do that is we can take those memory addresses and basically figure out the offset of those to then determine, you know, where we have to position the shellcode, or basically where we have to position the appropriate return address from that function so that the instruction after that will point to the shellcode. That's what we're trying to get to. Now, we're going to actually use another Ruby script to help us in order to find the offset, and that Ruby script is pattern_offset Ruby, and we're going to paste in our EIP crash address. Okay, so this tells us that after 1036 bytes into our giant buffer here is where basically EIP crashed. So we know that we're going to want to get a return address before that point. Let's look at the difference between where EIP crashes and where ESP is pointing at the top of the stack. So that's 37, 69, 42, 36. Okay, so this lets us know that the top of the stack was pointing to just 4 bytes later from where EIP was. So that's good. So that's good information to know, because we're going to need that in order to create the next script. So now let's start working on the next iteration of our script. Taking these pieces of information that we have now, we can actually construct or modify our Python script to now find that appropriate return address. Right now, we've just created a giant buffer to kind of find out or pinpoint the areas that are appropriate for us to get our shellcode to execute on the stack.